There's a really interesting yet strange phenomenon that happens when you freely rotate an object like a textbook or a phone. Now, in an object of this shape, there are three directions, main axes that you can rotate one of these objects about. Using my phone, we can see that a rotation along the green axis here would correspond to a rotation like this, whereas a rotation along the blue axis corresponds to a rotation like this, and the red axis corresponds to a rotation like this. When you rotate your object about the green or blue axes, you see that it maintains its rotation very well. However, when you rotate it about the red axis, it does not maintain its rotation very well and in fact tumbles about the other two axes. There are two very good ways of explaining this phenomenon, one being geometric and the other being very algebraic. Starting with the geometric illustration, we take advantage of the fact that because we have no torque in the system, we have two conserved quantities, rotational kinetic energy and angular momentum. If we plot these two three-dimensional shapes in the same space, namely this one, the axes denoted by omega x, omega y, and omega z, then because these two quantities are conserved, the resulting vector of angular velocity must lie on the intersection of those two shapes. Here I've drawn the ellipsoid in the black on our axes in the blue, with the possible intersections between the ellipsoid and the sphere laid out in the red. If we designate an initial value for the omega vector on one of the ends, say over here, we see that by the intersection with the sphere, an initial vector value over here will result in an oscillation around the ellipse. Likewise, if we have an initial value on the top or the bottom, let's say right here, we will have the same oscillation around the bottom of the ellipse. However, along the third axis, we see that a starting value close to that axis does not result in an oscillation like the other two, but instead results in our starting vector slipping away from the original value. This makes sense with what we saw when we were flipping our phone or book, how there are two axes that have a very stable rotation, and one axis that has a very unstable rotation. This result is further verified when we take a look at the math of the system through Euler's equations of a rigid body. These are Euler's equations for a rigid body with zero torque. Notice how the time derivative of each component of angular velocity is dependent on the moment of inertias and angular velocities of the other two axes. Consider the case in which we have a lot of angular velocity in the omega x axis and zero angular velocity along the other two axes. In this case, we can see that all of these would equal 0. Notice, based on the equations, that although omega y and omega z are 0, if we gave a little kick in the omega y direction, this would result in both omega y and omega z being greater than 0, although initially very small. Because we have a small times a small, we can approximate omega dot of x to still be about 0. Thus, we still have an omega x that is constant. Let's now take the second two equations in Euler's equations. Because omega x is constant, these terms in brackets are constant expressions. For solving the system of equations for omega y, we get this resulting equation down here, which again, because omega x is constant, we have omega y double dot equals a minus constant term times omega y. So looking more closely at this bottom equation, if I sub x is either the largest or the smallest of the three moments of inertia, we will have an omega y double dot equals a minus constant times omega y, which we know that a cosine function solves that differential equation. Conversely, if I sub x is the intermediate moment of inertia, then one of these two expressions will pop out a negative sign. This will actually give us a differential equation that is a omega y double dot equals a plus constant term times omega y, which we can see would actually result in an exponential function. So now it makes sense why the intermediate axis theorem, which essentially states what we just found, why it is named what it is. Because given an object like my phone, like we explored earlier, if we rotate it about the axis that has the intermediate moment of inertia, it is unstable. Whereas if it's of the largest or the smallest moment of inertia, it is a cosine function and is stable. It will restore itself. Now let's look at a program that mimics this system and will allow us to take a closer look at angular momentum. Before we take a look at the program, I first want to point out that I have assigned 2 units of angular velocity to the axis that corresponds to the intermediate moment of inertia, and I've also assigned 0.001 units of angular momentum to the axes corresponding to the 2 extrema moments of inertia. Now, unfortunately, the recording software is kind of messing with the graphics, and there's a lot of lag, but we can still see that it's rotating as we expect around the red intermediate axis. Now, I just want you to pay attention to the book, this watch it through again, but we can see that it is rotating about how we expect it to rotate, how we experienced it when we flung our phone or our book. Now, taking a look at these vectors over here, I have taken the components of angular momentum corresponding to each of the 3 axes over here by color. I've taken those out of the body frame and brought them into the lab frame. And you can see how the total angular momentum represented by the yellow arrow is comprised by these 3 angular momentums. And we'll watch it through one more time here. This watch through, I want you to pay closer attention to the graph that I have down here. Just like the vectors up here, I am using this graph to represent the magnitude of angular momentum along each of the 3 axes, again corresponding by color. It's kind of cool to notice how the angular momentum flows through the 3 components while still adding up to a constant angular momentum up here represented by the white. Energy is also graphed up there, and we can see that's constant, but the 2 lines are overlapping each other. Another interesting thing to notice, if you didn't notice the last watch through, is that the angular momentum in this graph, in the body frame, seems to be very periodic. I did not explore this any further, but it would be a cool thing to look at in the future. And I'll just let it finish playing out here for you, reaching the top. Now this time, just as a check to make sure that the program is working as it should, I'm going to give, or I'm going to switch up the amount of angular velocity I'm giving to each of the other 2 components. Now, if what we saw in Euler's equations and with the geometric representation are correct, given this layout of angular velocity, we should see that the rotation is cyclic. Now this time, let's keep our eyes on both the graph and the book. we can see that the angular momentums in the yellow and the blue direction are, as we expected, some sort of cosine or sine function. This is good. This is exactly what we expected. And we see that angular momentum and energy are both conserved. And lastly, we will just make sure that we see the same for a dominant rotation along the other axis, that we should also see cosine or sine function behavior down here, and we should see the rotation restoring itself up here. And this is exactly what we see. So using Euler's equations, we have kind of debunked this mystery.